I'd like to thank very much for the organizers, Dimitri and the other organizers, for the invitation to participate in this workshop and to present some of our work that we have been doing in the University of Rio de Janeiro, Federal University of Rio de Janeiro. The description of the quark-gluon plasma is something very complicated, very non-trivial, and at the same time fascinating. It's a long time that people have been using holography, holographic models to describe some properties of the quark-gluon plasma. The most important, the initial work in this direction was by Sons, starting at Scoveton about the viscosity of the plasma. There was no other way of calculating viscosity of the plasma, and they found a very interesting result using ADS-CFT. From that time, a lot of work appeared in the literature concerning the description of the quark-gluon plasma using holography or ADS-KCD holographic models that are phenomenological models inspired in ADS-CFT. What I plan to do here is to present some results concerning the importance of studying heavy vector mesons inside the plasma as a tool to describe the properties of the plasma. But then I want to focus in something that is more new results concerning this study of effect of rotation in a plasma. This is something that was not studied till recently. There is a lot of material literature about the effects of temperature, density, magnetic fields, but rotation, that is also an important issue of the plasma, important property of the plasma. Only recent have received more attention. So we have some new results about this that I would like to tell you. When you have these collisions of heavy ions, you form this new state of matter that behaves like a perfect fluid. And there are some very interesting aspects about this. One of the important facts is that you do not observe the plasma directly. You just see a huge amount of particles that reach the detectors after the plasma disappears by the hadronization process. So in order to understand the properties, how was the plasma, what was the temperature, the density, or any other properties of the plasma, you have to reconstruct the plasma from the particles. So it is of fundamental importance to understand how the properties affect the spectra of particles that you observe, so that you can you can really reconstruct the state that was formed and then hadronized. And one of the important issues that was proposed by Matsui and Zatz some long time ago is that when you form the plasma, or when you have the collision, there is one very short period of time where you form a lot of particles, many hadrons, and then after a short time scale, this system thermalizes and forms a medium in some approximate thermal equilibrium at some temperature. And this medium is formed mainly by the light flavors, by the dissociation of UDS quarks. But in the collision, you also form heavy mesons, you form particles made of heavy quarks like charmonium, bothonium. And these particles, they have a much stronger interaction, so the screening produced by the medium do not dissociate these particles completely, or actually it depends. They may be partially dissociated or completely dissociated depending on the temperature, on the density, and on the other properties of the medium. So we can look at the fraction of states of heavy quarks like charmonium and bothonium that are produced in a collision. And looking at this fraction, we get some information about what was the temperature of the plasma, what was the density, the magnetic field, and more recently we are studying the effect of rotation, because when you have a non-central collision, it is clear that you have a strong magnetic field, no? Because you have these charges with ultra-relativistic velocities, but also you have a rotation, vorticity, so, and all those things contribute or have some effect in the dissociation of heavy mesons. Okay. As I said, these heavy mesons, charmonium and bothonium, they only partially dissociate. And the intensity of the dissociation depends on the temperature, on the density, on the presence of magnetic fields, and also on the rotation. And rotation is something that have not been studied up to recent times. Okay. What are these kind of holographic models that you use? There are something very simple. You take into the theta space, okay, ADS, ADS-FT, in ADS-FT you have ADS due to conformal field theory. You want to describe a physical theory, quantum chromodynamics in some special regime. And so you don't want to have conformal symmetry. So we break conformal symmetry in some phenomenological, effective way by introducing energy parameters, okay? And fitting the results to what we observe in nature. Is the kind of approach that some people call bottom-up ADS-QCD. There is this top-down that will come from solutions of string theory, that bottom-up, you look at physics, how it is, and find models that reproduce the physics, okay? Yeah, the initial model was extremely simple, this hard wall model, and then there are some other kinds of model. I will not be talking about all of them. And then you can use holography, including the properties that we want to reproduce, that are properties of the medium. First, the temperature, obviously, but then we can also include the effect of finite density by using Heisner-Nordstrom, charged black hole. You take the solution of the charged black hole, and there is a simple way to associate the charge of the black hole to the density of the medium. So you have a holographic representation in which you use a charged black hole, and the charge is proportional to the density, so you can represent holographically a thermal medium with finite density or finite chemical potential, okay? It's also possible, it was shown in this paper and some others, to include the magnetic field effect. If you just include some magnetic fields in the background, you have some 5-dimensional magnetic field, and you map it to some boundary value of 4-dimensional field, that is the magnetic field of the plasma. And then this is the more new thing that I want to focus, that is how to include angular momentum, rotation effects of the plasma. What is the effect of rotation of the plasma in the confinement, deconfinement, critical temperature of the plasma? What is the effect of rotation in the dissociation of bothonium inside the plasma, charmonium? Do they dissociate more or less intensity? The intensity increases or decreases of rotation? This is the kind of thing we wanted to study. But the first thing is that it's clear that when you have a non-central collision, the rotation, the vorticity is something highly complex. You don't have a uniform rotation. But this is the same thing that happens for magnetic fields. Magnetic fields also, when you have this collision, your magnetic field is non-uniform, clearly. And if you look at works that study the effect of magnetic field, like magnetic catalysis, changing confinement, deconfinement temperature by a magnetic field, most of the works, or maybe all, I'm not sure of all, but most of the works consider a medium with a uniform magnetic field, because this is the easiest thing to do. And then if you know the effect of magnetic field, if it's not uniform, okay, you can evolve then, include more non-uniform effects. So for rotation, it's the same thing. If you consider a general rotation, it would be more difficult. So we will consider a very simple rotation to have for the beginning. But just a highlight what are the spaces that we use that I mentioned in the previous slides. First, this is the ADS Schwarzschild, but with charge. This is the case of temperature and density. You have just a black hole where you put some temperature and then a charge, and then the charge is related to density. If you have finite temperature and background field, also you have some factors here, just different black holes that holographically represent properties of the medium, density, temperature, magnetic fields. Okay, and what is the model we use for representing heavy vector mesons? Heavy vector mesons, they depend on more energy scales than the holographic models for light mesons, for row meson, for example, the soft wall model. They have just one energy parameter because the masses of the light quarks is very small, so most of the mass, or the mass of a light meson, like the row meson, you can associate only with the string tension, with the intensity of the strong interaction between the quark and antiquark. When you look at heavy meson, this is a very different situation. The mass of the heavy quarks is not negligible with respect to this energy associated with the string tension. So we must include at least one more parameter that does not come from strong interaction. It's not strong interaction that give you the mass of the charm quark, the mass of the bottom quark. It comes from outside of the realm of strong interaction. So we need more of this. And also there is an important property when you want to study thermal properties of heavy mesons in a plasma, that is the decay constant associated with the process of non-hadronic decays of heavy mesons. And this involves an interaction that is not a strong interaction. When you come from you transform a meson in a pair of E plus E minus. So we developed a model. There is a lot of technical details that I prefer not to mention, to reproduce the spectrum of bothonium. An interesting thing about these heavy quarks, these heavy mesons also, is that when we model light mesons, glue balls, all this kind of particles, there is a little experimental data, not so precise, so you can find any result and it looks fine. No? But when we look at heavy mesons, we have a great challenge. That is the fact that you look at PDG and you find very precise results for masses and also for decay constants. Decay constants are not directly there. They come from using the amplitude for E plus E minus decomposition or decay of the heavy meson. But you have very precise results for decay constants and masses for heavy mesons. So building a holographic model for these particles have this very strong constraint. Your result must fit in very sharp, very precise results from experiments, because these heavy particles, they give much more traces, much more easy for the experimental people to find the properties, because they don't get mixed with a lot of other particles like it happens with the light mesons. No? So it is interesting, but at the same time, it is somehow challenging. to find the correct answer. What is the kind of thing we find for these particles using this model with some field? We have a field living in a background, okay, and these fields are dual, normalizable. The fields are dual to the states or quasi-states in the case of finite temperature, to the states of heavy mesons. In the case of charmonium, for example, this plot, this blue line is the spectral function for charmonium at a low temperature, 150 MeV. There is a strong peak and a second peak corresponding to the second excited state. There is some thermal width. And then if you increase the temperature, go to this orange curve, then to the green curve, what happens is that the peak of the spectral function gets smeared, the width enlarges, and the height decreases, and also the thermal mass, that is the localization of this point here, changes a bit by the effect of the medium. And then at some temperature, you find complete dissociation. So by this kind of simple model, we are able to represent the situation and find the temperature at which charmonium would be completely dissociated. And the same thing for bothonium. Bothonium is more interesting because the interaction is more strong, and then they dissociate at higher temperatures. So the effect is much more strong, and even for low temperatures you find it easily. 3 peaks in the spectral function, 3 states of bothonium survive at low temperatures, then you have 2, then 1. So this kind of information tells us, okay, if I know the fraction of bothonium that I observe, that means I compare a process of a heavy ion collision with a process of proton-proton collision, where we think that there is no plasma. That's a non-trivial question, but okay. And then we can look for the effect of the medium in the dissociation process and get some information about the temperature. But the non-trivial aspect is not that it's not the temperature only that affects dissociation. Also magnetic fields, density, rotation. Okay, this is an example of the effect of chemical potential. These plots are of increasing chemical potential. As you increase chemical potential, the peak decreases, so the chemical potential has the effect of increase the dissociation of the meson in the plasma. The same thing for bothonium. This blue peak is the one with the no chemical potential, no density, and then the other ones are increasing chemical potentials. So chemical potential or density of the medium enhances the effect of dissociation.
So these are holographic results? These are
holographic results. We take this model that I present, the background, this is magnetic field, so that background corresponding to magnetic field, and we write a field, we include a vector field that represents the meson, and calculate the spectrum of states of this. And we find this spectral function. Yeah.
So what is the difference between charmonium and bothonium in this case?
Bothonium decreases, has much higher peaks because the interaction is more strong. So it dissociates at higher temperatures. Oh, to the different particles using different parameters. Let me, thank you. Thank you. Yeah, what happens is that for charmonium, we have a field, we have this general field here, this phenomenological background that we put in the middle. For charmonium, we have these parameters. For bothonium, we have the other parameters. But how do we find these parameters? We find them fitting masses and decay constants that we get from PDG. That means we look at the zero temperature spectrum of charmonium and find the parameters. We look at the zero temperature spectrum bottomonium, fix the parameters. Then we take these parameters that are fixed from zero temperature and use them changing just the metric, including temperature and magnetic fields. Okay?
Can you motivate a little more this function phi, so your dilaton as this phi of z? I mean, how did you arrive at those terms? Why do you know that they have exactly?
Yeah, this is this first term is something is the soft wall model, well known.
Okay.
And the other things were based in looking. You can write the equation of motion in a Schrödinger-like form. You have some potential, and you have to look at the form of the potential. How is it affected by functions that you do here? But summarizing just by trying something that works. It's phenomenological.
And may I ask another question? I mean, you know, people did this for the lighter mesons like Charm or Strange and you and works a long time ago. So why do you know that now you are talking about heavy mesons rather than light mesons? Just the answer is the same, yeah, because you just fit these parameters to. Yeah,
for light mesons, as I explained before, the mass of the quark is negligible, so it's much simpler. They have, or for example, if you look at the spectrum of the rho meson, you have something almost linear like you have in the soft wallpaper. If you look at a heavy meson, you have something like more like this, because of the first state has the contribution of the mass. And then you have this jump associated with string tension, but you have the light mass. So you must have more parameters to describe you. Oh, we didn't consider chiral symmetry. We have an explicit, we have a large mass for the quark. So we are not looking at this light flavor sector. We just wanted to look, and why did we want to look at heavy mesons? Because heavy mesons give some important information about the plasma. Modeling heavy mesons is different, really, because of this large mass. And then you have to find a different model for it. Okay? So we have this spectral functions, effect of chemical potential, effect of chemical potential in bottomonium, and the effect of magnetic fields also. Magnetic fields also change the, enhance the dissociation. And depending on the direction of the field with respect to the polarization. Yeah. And how do we include the rotation, the effect of rotation? Okay, as I said before, the vorticity of this plasma formed in a non-central collision is something very complicated, very non-trivial. You have the Lorentz contraction, so you have like two pizzas that collide, and then it's not. Okay, but we follow the same line of people follow, and we have done this also when studying magnetic fields. Let's consider first the most simple example. What's the most simple example of a rotation? Oh, let's take just a circle, just a cylinder, when you have rotation, but all the particles rotate with the same speed. So, okay, we will analyze the effect of the speed, but in a simple situation. Then we move one step further and so on. To do this, we consider an ADS space with cylindrical boundary. We change it to this, like compactifying one of the boundary spatial coordinates and writing a cylinder. This does not change the curvature of the space, so it is ADS, okay? If you compactify 2 dimensions, things are different, but compactifying just one, no problem. So we take the cylinder, And then we make a transformation of coordinates. And transformation of coordinates in such a way that we have a new metric produced by this rotation. And this new metric, if we calculate the angular momentum for this metric, okay, we have a non-trivial angular momentum. Huh? And the Hawking temperature is changed. And if you look, now I'm looking just at the plasma, not yet at the heavy mesons, just at the plasma. We found that we want to look at the transition, a critical temperature of the transition, confinement, the confined phase, the confined phase. If you just put pure ADS space, you don't have any transition. You have to put some energy scale, use some model like soft wall, hard wall. And then using soft wall or hard wall, we find that the critical temperature decreases with the factor that is just Lorentz factor. That's some result that we published recently. This result is somehow trivial because, okay, so if you have rotation, you get the Lorentz factor. Just this is a bit trivial, no? Okay, but we have some non-trivial results if we go some steps further. There are two directions, important directions. First, to consider a rotation of a solid body, something that is not just a circle, but we have consider different speeds, no? And another thing is that if we combine the effect of rotation with the effect of density, okay? Okay, let me first talk about this part of density. In this recent paper, we analyzed the combined effect of finite density and rotation using this soft wall, hard wall model. Soft wall is just that field that I showed you, but with the first term, K2, K squares, Z squares, an old holographic model. Okay. In this case of combining rotation with density or chemical potential, you find some non-trivial aspect. Because when you apply the rotation, you start with this metric, this the Eisner-Nordstrom that has some metric, some field, gauge field that will correspond, the boundary value will be equal to the chemical potential. But when you apply the rotation, you rotate the metric, but also the field. And so there is a change in the density produced by the rotation. And this effect leads to a result in which the effects of rotation and density do not factorize. There is some combination of the effects because after the rotation, the transformed density gets also transformed by the Lorentz factor. And we find that the critical temperature for confinement, deconfinement, transition, this is the critical temperature as a function of the chemical potential divided by some constant of the model, okay, but chemical potential. And these colors correspond to different rotational speeds, okay? And we found this kind of result, that the rotation decreases the critical temperature as density also, but not by factorized factors. No? We have some combination. Well, one important thing is to look at some result that we could compare with. We always try to compare our results with lattice, or when there is some experimental result. In this case, no experimental result. The chemical potential that uses the quark chemical potential, but we can calculate from it, it's trivial, just a factor of 3, the baryon chemical potential. And for these two models, we calculated the critical chemical potential. What is this? Is this point, set of points, this point here, but yeah, equivalent to, without rotation, yeah, it's not in this plot, but these critical values correspond to what is the value of the baryon potential such that your medium is deconfined, or there is a medium if it is the matter is deconfined even at 0 temperature. This is the critical density, the confinement at 0 temperature. Okay, and we found this different values depending on the model, 1,200, 1,300. Can we compare this with anything? Yeah, we can. We have lattice representation of this kind of problem by lattice is non-trivial, but we have some very interesting result concerning the dependence of the critical temperature, the phase diagram, QCD, quantum chromodynamics. An interesting point to observe that is that this region here is not a first order transition as we have, it is a crossover, but okay, we don't have crossover. But there is a plot by this lattice people of the critical temperature as a function of the baryonic chemical potential. And they don't reach this point of 0 temperature, but the region here is, we found 1,200, 300, so it's not something that is far from the order of magnitude of the results from lattice. So, yeah.
A question.
Oh, sure.
For high density nuclear matter, you have this idea that in neutron stars, the matter is superfluid. So you don't have that here. You don't have, your rotation is not of a superfluid.
No.
There are no vortices, nothing like that.
No, we didn't consider up to now this effect of vortices. Yeah, but it would be interesting. Yeah, thank you. Okay, another step in order to implement more a less trivial situation of rotation is to consider a rotation that is all the particles do not have the same velocity. And this is just the case of a disk. We take a disk, the disk is rotating. Okay, the particles in a fixed radius, they have the same velocity, but at different radius not. In this case, there is an interesting effect to be taken into account. Okay, thank you. Very good. This is the so-called Tolman-Ehrenfest effect. Tolman-Ehrenfest, they have studied the situation of thermal equilibrium when you have a system that is rotating, or somehow equivalent that is under the effect of gravitational fields. And they found this interesting expression for this kind of rotation here, that in order to have thermal equilibrium in the sense that the different shells of this disk will not exchange heat, so thermal equilibrium, the local temperature at each point of some radius r varies with this factor that is Lorentz factor. Okay? So you have some reference temperature that it's more simple to take the temperature here at this point of the center of the disk that is not rotating, and the other temperatures are larger because of this effect of no inertial effect. So there is a variation of the temperature in this medium, in this object in rotation. And we can go back to the description that I just showed you of a rotating cylinder and take a combination, continuous superpositions of different cylinders in order to map holographically what would be a disk like this. With some subtlety, we have a set of holographic mappings, one for each radius. And in order to reproduce this result of Neumann-Ehrenfest, we have to superpose cylindrical shells, each one, all of them with the same reference temperature. That would be the temperature of the rest, plasma at rest. And doing this, we find a local temperature varying with the radius exactly as found by Neumann-Ehrenfest. And with this situation, we find something very interesting. That is the fact that you may have a non-homogeneous medium depending on the reference temperature, the temperature in the center. It may happen that the reference temperature is greater than the critical temperature of the transition. Then all your disk is, contains just deconfined hadronic matter. Or it may happen that the highest temperature that is reached locally, that is the temperature on the boundary of the disk, that is the point that rotates with the highest speed, if it is smaller than the critical temperature, inside the disk, all the particles are confined, the hadrons are confined, so there is no plasma, there are just hadrons. But you can have a situation in which the local temperature at some intermediate radius, I call RC, critical radius, at this point the local temperature is the transition temperature. So inside this region you have the hadrons and outside the plasma. So you find something non-trivial, that is the possibility of having a non-uniform, a non-homogeneous medium in which part of it is a plasma, part is not. So rotation may imply some non-trivial effects in the plasma. And that is very important when we want to reconstruct. Now, for describing rotation, there is some alternative way that is using the Myers-Perry black hole that has angular momentum in it. And this could also add more effects to the vorticity and things like this, but the problem is that this Myers-Perry black hole, you have a compact boundary, you have to make some mapping to a flat boundary to represent the real quark, the quark-gluon plasma, and this mapping is non-trivial. We have been studying this. Okay. And an interesting result found work with Young, that is here, is the student, is the effect of rotation in bottomonium spectrum. If you take bottomonium spectrum without any rotation, we have these two peaks corresponding to two states at temperature 200 MeV. And then if you increase rotation, this omega L is just the speed of rotation, angular times radius. And then increasing the speed of rotation, the dissociation effect enhances. So rotation, it's simple to understand because you have a higher local temperature by the Neumann-Ehrenfest effect. So rotation increases dissociation, and this must be taken into account when you have to reconstruct the plasma just looking at the bosons, the bottomonium states that you find in the detectors. Okay. One thing I would like to comment before finishing is that when you look at these models, as Dimitri asked me about the parameters, Johanna, we find this field. How do we find this field? And okay, but why does this kind of model work so well? They give results consistent with other calculations. what is the reason why these 5-dimensional fields in some particular background represent the mesons? Mesons are 4-dimensional particles. When you want to represent electrons, it's very easy. You have quantum electron dynamics, a 4-dimensional quantum field theory, and that's nice. Why do I use 5-dimensional fields? It's simple, because the meson is not an elementary particle. It has a structure, quark into quark, and there is an interaction. There is some effective separation, a potential between them, Cornell potential, and so on. And we have some recent works in which we look at this background that we use. In the previous works, we put some field inside a background and calculate the spectrum. Okay, that's it. In these new works, we took this background and put a string in the background, like Baldacena did in the seminal work about quark-to-quark interaction, that in his case it was conformally symmetric, so just one over a distance. Okay. But we took a string, we put a string fixed on, with 2 points fixed on the boundary representing the heavy quarks, and calculated the energy with the background that we use for calculating properties of the mesons. And what shows up is that we find, using this, we find a potential interaction following the same approach as Baldacena, but with this background modified. We found a linear potential, and a linear potential with a coefficient that is consistent with the Cornell potential coefficient, and more than that, when we increase the temperature, the string tension decreases, and we find dissociation at the appropriate temperature. So this means that the background that we use to represent mesons is a background that is representing internal structure, the interaction between the quark and the antiquark. It reproduces the way that these particles interact, the potential, the dissociation, and the temperature increase, and so on. And that's why the model works for capturing the properties of the mesons, because it's really representing the structure of mesons that are not elementary particles. Okay? That's why I use a 5-dimensional approach or fields. Okay, that's something that I already explained. It's possible to reproduce the dissociation, factor of density, magnetic field, and rotation, and the confinement temperature, and so on. And okay, thank you very much. Thank you.
Questions?
Yeah, very nice, thanks. I mean, there's been a lot of interest in experiments now for the quark fluid plasma in looking at rotation fluids, but I'm not really up to date anymore with these now. So I mean, you said you're not really aware of any measurements, but I could imagine that, you know, these heavy quark states have been investigated at, say, RIC also in the rotating plasma, and I don't think so.
I'm sorry, I didn't.
Sorry, maybe I should speak more clearly. Okay, so there was a lot of experimental interest in rotations of the quark fluid plasma recently at RIC.
Yeah,
okay.
At RIC. Yeah.
So you were saying that you are not aware of any experimental results, but I would imagine that people studied quarkonium states.
Not this kind of results for the degree of dissociation of bothonium, for example. Okay. The results are different. The results from RIC, there is a way of measuring the angular velocity using the, there's some interesting result that, I mean, there's also you look at the polarization of some of the particles that you measure, and from these you get the rotational speed of the plasma. Okay. Yeah. So I should correct what I did. There is information, experimental information about rotation, And it's very important because we can use this to estimate what's the angular velocity of the plasma. It comes from the polarization of some of the particles produced. It is affected by the rotation. There are some experiments. What I said, what was not studied was how does the bottomonium spectrum is affected by rotation, just this. But there are some very important results. Thank you very much.
Yeah, but there's also this chiral vortical effect, where you see this dissociation of, depending on the helicity of the particles, essentially.
Yeah,
that should maybe also have an influence.
We want to improve our models to include this kind of vorticity effects, local vorticity. There are some important works by Chernobyl about this, and we want to improve. This is just some initial simple study.
Okay.
But thank you very much.
Yeah, thanks a lot.
Any other question? Okay, then thank you again.
Thank you very much.